Welcome to lecture 5. So today we'll do a slightly more complicated programming language for which there is also a compiler. But before that, let's briefly summarize what we did last time and also answer the question. So we'll follow more or less the same abstraction levels, except that this brown I'll change. So programs and commands and atomic commands and a context-free grammar notation will remain the same. So let's look at last time's grammar. We had this grammar. Firstly, the grammar of programs was that every program is just a command. A command could either be some atomic command or it could be a sequence of commands, or it could be a conditional with an if, B, then C, else C, phi, where all these words in black are reserved words. So including this, which you may not have seen, it acts as a closing bracket for the if, and similarly the odd here, it acts as a closing bracket for the do. Okay, so one of the things I said was, we also defined the notion of ambiguity. For example, we saw that this grammar, so for example, we asked the questions whether this given grammar was ambiguous. So as I said, a grammar is ambiguous if there exists a sentence in the language generated with more than one parse tree. It's implicit that if a grammar is ambiguous, not only will its parse tree be, not only will there be a sentence with more than one parse tree, the same sentence will also have more than one abstract syntax tree, because the abstract syntax tree is just obtained from the parse tree by elevating the operators to the root nodes and replacing the non-terminal symbols by the appropriate operators. Yeah, that is for a restricted class of parse trees. Okay, so the question was how this grammar is ambiguous, and actually in the case of these two control structures, the conditional and the loop, I have eliminated the ambiguity by introducing two new reserved words, the closing bracket words phi and odd. However, this sequential composition or the sequencing operator, which is a binary operator on commands, actually gives you ambiguity. So let's see how that happens. So for example, you could have three commands. So let's assume you have C1 semicolon C2 semicolon C3. These three are either atomic or compound commands, I don't care, but these three commands actually give you two different parse trees. So you could, for example, you could have a parse tree like this, I am drawing triangles here to denote that these C3 these various commands themselves can expand into trees. So this is a tree in which this first semicolon is the root and the second semicolon is the right subtree, is the root of the right subtree. Right? Another possible parsing of this is the following. You could have a semicolon C1 C2 C3, in which case this the first semicolon is actually here it forms the root of the left subtree, and the second semicolon is the root of the tree. So strictly speaking, there is ambiguity in this grammar, but what we will see, and what is obvious actually to anybody who has done some programming, is that the sequencing operation in any programming language is associative, in the sense that this really, these two trees really correspond to different bracketings, right? So this tree, for example, corresponds to the bracketing where you have C2 and C3 bracketed inside and C1 and C3 bracketed outside, and this tree corresponds to the case where you have C1 and C2 bracketed inside and then C3 bracketed outside, right? So this corresponds to C1 semicolon C2, the whole thing semicolon C3, and this corresponds to C1 semicolon C2 semicolon C3, right? But since in general the sequencing operation, as we will see later in the semantics, is really a function composition operation, and the function composition itself is associative, we will see that sequencing is also associative. So what it means is that as far as the implementation of the language is concerned, any implementation can take any decision with regard to the semicolon operation. So the fact that it is ambiguous does not matter as far as the runtime behavior or the meaning of programs is concerned. Yeah, so that's a small matter which we have disposed of, but in other cases things can change, as we saw an example of Boolean expressions where there was ambiguity if you did not introduce parenthesis, and it can actually change the value of the Boolean expression depending upon how you parse the Boolean expression, right? So let's look at how, if you were to actually look at a language reference manual, what would it look like? So we have, so most languages since Algol 60 use a notation called the Backus-Naur form. Okay, it's actually a notation created by John Backus and Peter Naur in the definition of Algol 60. The Algol 60 report was the first language which used a rigorous syntactic form based on context-free languages and context-free grammars to define the language accurately. Before that, for example, Backus was involved in the creation of Fortran, and the net result was that since there was no clear syntactic definition of the Fortran language, every Fortran compiler written by various people gave different interpretations to the syntax of Fortran, and what that resulted in was that Fortran programs were not compatible across machines. So for example, the way one compiler treated the Fortran syntax was different from another compiler, and moving programs from one machine or one compiler to another compiler became a huge problem. It became a huge problem in the sense that you required a whole team of programmers to actually either entirely rewrite that program to suit the new compiler or the new architecture of the machine, or it required substantial rewriting and patching up of programs so that they would run correctly on the new machine or on the new compiler. Okay, so by that time, of course, context-free grammars had become quite popular as a form of theoretical study, and Backus and Naur defined the Algol 60 language using this notation. They were, well, as far as we are concerned, what they used was, to ensure readability, they did not use non-terminal symbols. I mean, they did not use single character non-terminal symbols. They used full words. So they wrote statement within angle brackets, and since there was no arrow mark on the typewriter, they used a double colon equals, which has now become standard. Okay, and so they wrote all the productions in this form in full, with the non-terminals being enclosed in angle brackets and the arrow being replaced by double colon equals. But actually what is more convenient, and which came up very soon, is what is known as the extended Backus-Naur form. Okay, the extended Backus-Naur form, it just adds the power of specifying regular expressions within context free in a convenient fashion. That's all. It's merely a convenience. We should remember that firstly, regular expressions are also context free, but what happens is that there are many constructs which, for example, allow for options or 0 or more occurrences, and in order to specify them by a context free grammar with the limited notation that we have, what it means is the introduction of new non-terminal symbols to allow for those kinds of iterations. So the extended Backus-Naur form essentially uses the Backus-Naur form extended to include iterations in choice. So for example, so here you have one thing. So let's look at this. So supposing you had a Backus-Naur form production of this form, okay, where alpha, beta and gamma are strings of terminals or non-terminals. Okay, so if you had a production of this form, A goes to alpha, note that as usual I am using my light brown brackets for the notation, for the Backus-Naur form notation, or for the context free grammar notation. Yeah, so this would be equivalent to the two productions, A goes to alpha, B gamma, where B is a new non-terminal symbol which is not already there in your set of non-terminals, and B either goes to epsilon or to beta, right. So this just says this is something, this notation, the extended Backus-Naur form notation, is something that you will see quite often. For example, on any Unix machine, if you run the man pages for some command, so you will find that there are various options given, switches given, and they are usually separated, they are usually enclosed in brackets of one kind or the other. Normally they use square brackets to represent the various options. So a typical example would be that, for example, if you had more than one option, as in this case, the two options, the several options are either separated by bars or they are separated by commas, and what it means is that this is equivalent to this set of productions with a new non-terminal symbol. And since in the definition of a programming language you do not want to clutter it up with new non-terminal symbols which do not have any particular significance, okay, except that they aid in writing out a grammar more systematically. If they do not have any logical significance, you wouldn't like to introduce them, right. So for example, if you had the option of having an if in a language like Pascal you allowed both statements, both the if then statement and the if then else statement, then the else clause is an option, okay, which ideally could be separated out, but then the else clause actually belongs with the if and the then as a grammatical entity, so you wouldn't like to separate it. And so what you would do is you would put that else clause in the definition of your language. If your language allowed an else clause and a normal one arm conditional like if then, you would put the else clause within these square brackets, right. So that you reduce the amount of the number of non-terminal symbols. Remember that a programming language, a real world programming language which is actually being used, is actually quite a large piece of syntax by itself. Without actually complicating it further, by adding these extra non-terminals which do not have any particular significance. Yeah, so which have significance for the compiler, which have significance for accurately specifying the language, but otherwise do not have grammatical significance. Yeah, so which have significance, for example, with respect to ambiguity, parsing, and so on and so forth, but do not as a logical entity have a separate significance from the non-terminal in which they have actually specified as an option, right. So the other thing is that you can have 0 or more repetitions of some option. So if you were to have a production of this form, A goes to alpha within braces beta gamma, then this is equivalent to saying that you have two productions of the form A goes to alpha B gamma, where B is a new non-terminal, and B is, this denotes 0 or more repetitions of the string B in your production, of the string beta. So B either goes to epsilon, which denotes a 0 number of repetitions, or it goes to beta B, so that you could have more than one occurrence of a beta, right. So this is the extended BNF notation which is normally used. The extended BNF notation is also very convenient for other practical reasons. For example, if you look at any Pascal manual, the syntax diagrams of Pascal are directly equivalent to the extended BNF notation. So you just have to follow the arrow marks in the syntax diagram and they actually give you the productions, okay, and they correspond more to the extended BNF notation than to the ordinary context free grammar notation that we have already seen. So it's important to know this for sorry, for reading manuals, for learning a new language, and also for maybe and in general to know about the language, right. So let's look at a language. The last time we looked at a toy language which didn't even exist. So let's look now at a language which actually does exist. So this is the language PL0. This language is very much Pascal-like. It was designed for the purposes of teaching programming languages, compilers, and so on, as a first course by Nicholas Wirth himself, the designer of Pascal. He has also written the compiler, which is available with us. So the main thing about PL0 is that it is even smaller than Pascal. It has a single data type. The main features are that it has a single data type called of integers and nothing else, no other data types. The only control structures are assignment, a sequencing, bracketing, looping, and a one-arm conditional. That means it has an if-then statement. There is no if-then else. There's just an if-then statement. You can program an if-then else as two one-arm conditionals in sequence, right, where you can negate the boolean. Of course, there are no boolean data types in this. What it means is that you will have to encode your booleans maybe as integers, okay, maybe use 0 for false and 1 or anything greater than 0 for true, okay. So but it does contain one important feature, and that is a control abstraction mechanism. So it actually contains parameterless procedures which allow for a stepwise refinement of programs, which allow for an abstraction of which allow for complicated programs to be written in a structured fashion, and it allows these parameterless procedures also to be nested. Okay, so you can have a nesting, so which allows for a stepwise refinement in the development of programs. So let's look at the syntax of PL0. Let's look at so I will keep using the arrow mark instead of the double colon equals for a production, but I'll use the extended BNF notation otherwise. Right. So let's define it in a top down fashion. So a program, my start symbol is P in this case. I will not explicitly specify the terminal symbols and the non-terminal symbols. I'm sorry. I will not explicitly specify the terminals and the non-terminals. It's obvious that the terminal symbols are those that are colored black, and the non-terminal symbols are others. Yeah, and so the start symbol, however, is P. So a PL0 program is a block which terminates with a dot, with a period. This is as in the case of Pascal programs, you terminate the program with a dot. Right. A block consists of a declaration followed by a statement. I'm saying a declaration and a statement. We'll see that. So a declaration, and also for brevity, I don't write full names for the non-terminals. I have tried to use non-terminals. I have tried to use single letter non-terminal symbols, which are sort of obvious what they mean. So a declaration D can be, this clause is optional since it's enclosed in light brown brackets. So you can have a constant declaration. Okay, a constant declaration, which means that, so this word const is a reserved word. Okay, and a constant declaration is, I have put these in dark brown, I and N. They stand for identifier and number, which we'll look at later. The reason I have put them in dark brown is because they're not really non-terminals. I mean, there could be an infinite set of identifiers possible, and of course an infinite set of numbers. We are considering an ideal machine for which we are specifying the syntax. The actual limits on the numbers and the lengths of identifiers is going to be implementation dependent. Right? That is not part of the syntax definition of the language. Right. So they are not really non-terminals. They are actually terminals, but then there are an infinite number of them possible. So we'll define them also, but for the present, just take this this dark brown I and N at face value as identifiers, that is names, and numbers. Since we have only integers, those are the only kinds of data type we have, and of course you could have a number of constants specified, separated by commas. So the comma is a reserved word of this language, and the moment the word constant occurs, there has to be at least one constant definition. Okay, so this combination specifies one or more occurrences of the clause I equals N. This also specifies how they should be separated. They should be separated by a comma. If there is a const reserved word, it should be terminated by a semicolon. So you can define a sequence of constants in a single declaration and terminate that sequence of constants, terminate the entire declaration by a semicolon. And of course you don't need to have any constants at all, so this entire clause is optional. Okay, now whether you have any constant declarations or not, you could have variable declarations, but you don't need to. So even that clause is optional, and since there is only one kind of a data type, it's not necessary to explicitly specify what the variables are going to be of. So you can just specify the variables separated by commas, but the moment you have this reserved word var occurring, you have to have at least one identifier. If you have more, they should be separated by commas, and if you have this var, the entire variable declaration will have to be terminated by a semicolon. Okay, so this is also optional. You could have procedure declarations, and they are parameterless procedures. and a procedure has procedure as a reserved word. There should be an identifier which should be terminated by a semicolon, and there should be a block which is again terminated by a semicolon, and the entire procedure is also optional. You don't need to have any procedures in your program, and whether you have one or more of these clauses, they should occur in this order, and you have a statement. So I should not have written this. Sorry, let's erase this. We are just considering declarations. So declarations end here, and of course the entire set of, since this is optional and this is optional and this is optional, you could have an empty declaration too. So this production implicitly allows the production d goes to epsilon. Okay, right. So now let's look at the statement, which is S. So a block just consists of a declaration followed by a statement. So let's look at this definition of statements. So a statement itself could be empty, a declaration could be empty, which means an empty string itself is a program, but that need not worry you too much. That's a sort of a trivial case. But a statement could be empty. Otherwise you have an assignment. An assignment statement is a statement, where an assignment of course is an identifier colon equals an expression. Note that there is absolutely no relation between what identifiers are declared in this declaration and what identifiers are used in the statement. So the syntax is context free, but the language feature is such that you cannot use a variable without declaring it. Okay, so that is something, that is a context sensitive feature which is not specified in the syntax of the language. Yeah, okay. So then you have an explicit procedure call statement. Okay, so you can call an identifier, and the implicit meaning is that this identifier should have been declared as a procedure, otherwise you cannot use call. Call is a reserved word. You have the one arm conditional, which is if a condition then a statement. This whole thing is a single statement. You have the looping construct, which is just as in Pascal, and you have compound statements. You can coalesce a sequence of statements by bracketing them with a begin and end and call that a single statement. So this just says that you can have a begin, you can have an S. Note that since S can produce an epsilon, this could also be empty. Okay, then you can have 0 or more occurrences of this. So for example, just a pair of brackets begin end itself is a statement. It's a trivial statement which does nothing. Okay, it corresponds to a no operation, for example, in hardware. So you could have 0 or more occurrences of this grammatical entity, and they are all separated by a semicolon, right? And this whole thing is a statement, right? So now we have our previous if you look at the only non-terminals that are not really been defined here are I and N, which I will define at the end, but all other non-terminals here have been defined, but of course they have also they have also defined at the expense of introducing new non-terminals. Okay, so for example, expressions, conditions, these are some things that we have to define. So a condition, the language is such that I have modified the language a bit. Firstly, there is a unary condition which for any expression E, note that since the only data type available is integers, the only expressions available are also only integers. Okay, so this unary data type applies over all expressions. This unary condition, this unary predicate applies over all expressions and yields a true or false. So the reason for using this odd is, well, partly because, well, it's nice to have a unary predicate, some unary predicate. Secondly, this also, the reason for choosing odd is because there is a direct jump on not equals in most hardware. So wherever you have jump, or even in your high level programs, a large number of your programs are of the form while some variable is not equal to 0, do something. So in all those cases you could check for oddness of that variable, because a variable is also an expression, as we will see, and you could use this as a condition. So it's the otherwise you have various binary relational operators. Okay, I have simplified the original language to a certain extent by using single letter relational symbols. So that's why you have these odd looking symbols. Okay, so this is a standard greater than, this is greater than or equals, this is equals, this is not equals. It's the original Pascal compiler, for example, allowed this as a not equals symbol. This is less than, and this is less than or equals. The original PL0 compiler, as defined by Wirth, actually assumed that the less than or equals and the greater than or equals symbols were already available on the keyboard, which they are not. So I have had to change that. Okay, so conditions really depend upon expressions, either through unary predicates or through binary predicates. And let's look at the expression language. So before I get into the expression language, I would like to say something. See, here in the case of the expression language, you have a compromise between two extremes. One is, of course, that all of us think of expressions really in this form. Supposing you just consider the 4 operators that you have: addition, subtraction, multiplication, division. We normally think of an expression as being a sum of 2 expressions, a difference of 2 expressions, a product of 2 expressions, or a quotient of 2 expressions. And of course we use brackets. However, what happens is that this is ambiguous. This grammar is ambiguous because, for example, it doesn't use parenthesis sufficiently. It's possible to generate sequences which you understand to have a certain priority, order of evaluation, and which, if you define the expression language this way, the compiler need not. Okay, so it is ambiguous, and of course every variable is an expression, every constant, an integer constant, is also an expression. Those are the atomic statements of this grammar. So the other extreme is what we have already seen, and that is that you fully bracket every expression. Whenever you have a binary operator, you put a bracket around the pair of operands. So you can have e plus e enclosed in parenthesis, e minus e enclosed in parenthesis, e star e enclosed in parenthesis, and e div e enclosed in parenthesis. But however, most of us find it tedious to look at to actually write parentheses over everything. I mean, you will have to key in parentheses every time. Whenever there is a binary operator, you would have to key in parentheses. Okay, so as far as we are concerned, in our abstract language, in our abstract syntax, we will just, if we are looking at abstract syntax in string form, we will just assume them to be fully parenthesized. If you are looking at abstract syntax as in tree form, we will just draw the trees corresponding to whatever order of evaluations we want. okay, because any fully parenthesized notation can be translated into an appropriate abstract tree which preserves the order of evaluation of the expressions, and vice versa. Given any abstract syntax tree, you can transform that into a fully bracketed string of symbols, okay. But from the point of view of a compiler, this, because it's ambiguous, is clearly unacceptable. This, because it's tedious for every programmer to write fully parenthesized versions, makes it inconvenient. So what one has to do is that one has to strike a reasonable compromise and try to define the expression language in such a way that it is not ambiguous, it's not tedious, and it follows all the conventions of so follows all the normal conventions of mathematical notation. Yeah, right. In passing, let me mention that this plus and minus are also overloaded unary operators. For example, you can take negative numbers, or you can write positive numbers as plus something, right? So then they become unary operators, okay. So a negative number is just the unary minus of a non-negative integer, okay. So it's a unary operator there, whereas when it occurs in such a form, it's these plus and minus are binary operators, okay. So we have to take that into account too. There is overloading, and we always, in our mathematics too, we have used a lot of overloading. For example, in our programming too, addition, subtraction, multiplication, division, and multiplication are used for over both real data types and over integer data types. In the Pascal language, they are also used for set operations, okay. So they are overloaded tremendously, and this overloading is something that one should take care of. So the normal conventions that we follow are that unary operators usually bind the tightest, okay. That means a unary operator, its influence extends over to the first available symbol, and that's it, and it takes precedence over everything else, over all other operators, except when there are parentheses, okay. So if you have a unary operator and a large expression enclosed in parentheses, then it's the negation of that entire expression and not of the first symbol after the expression, after the left parenthesis, okay, right. And plus and minus are of course overloaded, and the normal mathematical convention is that multiplication and division bind tighter than the binary operators plus and minus, okay. However, multiplication and division lose precedence over the unary operators plus and minus. So if you have for example minus 5, if you have an unparenthesized expression of this form, minus 5 star minus 3, then or minus 5 star 3, then what you mean is that this minus refers to this 5 and not to the entire expression, this minus refers to this 3, and this star binds these two. So the appropriate bracketing is this, right. So we have to take these conventions into account for the purpose of for giving a friendly user interface as far as the expression language is concerned, so that people with a normal knowledge of mathematics, mathematical notation, mathematical conventions can write programs, can write expressions that they have normally been trained to write, right. So let's look at the expression language. So what happens is that the provision of this convenience means that you require a more a fairly large number of non-terminals before you can expect to define it unambiguously, right? So here it is. This language of expressions is available in all books which somehow or the other deal with parsing or compiling or anything. So I won't go into great details about how it is unambiguous and how they have taken into account all the conventions, but you can see it at a glance that it will work, right? So an expression is a term which might be preceded by a unary plus or minus, or since this is an optional clause, it may not even be preceded by any of these. Okay, so it might be an unsigned term, if you like, followed by optionally an addition operator and a term. Okay, right. The addition operators are just the binary plus and minus. Right. So please disregard this. Okay, so any expression can be regarded either as a term, a signed or an unsigned term, or a signed or an unsigned term with an addition followed by an addition operator and another term. A term is something which is either a factor, which we will worry about later, or it's a product of two factors or the quotient of two factors. So this M is a multiplicative operator. So star and division, the multiplication and division are multiplicative operators, and a term is something that of this form, either it's a factor or it's a product or quotient of two factors, right? A factor is anything regarded as a single unit. Either it's an identifier, which means that we are normally talking about variables or constants, or it's actually a number specified as part of the expression, or it's a whole expression in itself enclosed in parentheses, right? So you can see that these terms, that these three non-terminals E, T and F are mutually recursive, because E is defined in terms of T, T is defined in terms of F, F is again defined in terms of E. So they are mutually and circularly non-recursive, circularly recursive, and they actually take into account the fact that you can look upon, so if you can look upon an expression as basically the sum of two things, so you do not expand out into a term. So if you have that the outermost operation that is to be done is an addition operation, okay, you have some large expression whose root operation is an addition operation, that means that's the last operation to be done, then your context-free grammar generation is such that the left operand, supposing it's just an identifier, so your productions will allow it to go from E to T, then from T to F, F to I, F to E again, or F to I, and from I again it will keep circularly revolving. Yeah, okay. So we will so this grammar really takes precedence of operators into account, and the point is that this syntactical definition is absolutely essential for writing the compiler. So for pragmatic reasons it's necessary to have this kind of a syntactic definition, but semantically we will just look upon an expression as a signed or an unsigned expression, or something that is a binary operator, just in terms of abstract trees. So we'll either look at it, if you want to represent them linearly, either as fully parenthesized expressions or as abstract syntax trees. Yeah, so lastly, let's come to the last part, which is the definition of a number. So a number is either a signed or an unsigned integer. So this is an optional clause, and the definition is that it can have a digit, that it should have a digit followed by more digits. Okay, and a digit, of course, is defined as a character 0 to 9. Right? So an identifier, we follow normal Pascal rules. An identifier should start with a letter. In the case of the PL0 compiler, all the alphabet consists of only uppercase letters. It's very trivial to modify it to include lowercase letters too. But what really distinguishes a number from an identifier is the occurrence of a letter or a plus or minus symbol or a digit. That's what really distinguishes that. Okay, so the occurrence of a letter, this plus or minus really is an operation. It's not. It's not really. I mean, you're actually going to take. If you have a negative number, you're actually going to take the corresponding integer and negate it as an operation, right? Okay, so in the case of an identifier, that's why it should begin with a letter, and it may be followed by one or more letters or digits, right? And the reason for removing this n and I productions from the main grammar is that these rules are really not part of parsing. I mean, they are part of what is known as a lexical analysis. Okay, for example, you can write such rules also for recognizing that the word while, WHILE, has been recognized as a single word. The word begin has been recognized as a single word. So these are actually part of the process of what is known as scanning, okay, or lexical analysis. So typically, if you look at a program written in this language, it just consists of, it's a file of characters, and we would like to divide up the program into words, or what are known as lexemes, or which really describe each entity in the program. So instead of a file of characters, we would like to regard it as a file of words. And how are you going to regard it as a file of words? You should be able to recognize all the reserved words. You should scan all the words and decide whether they are reserved words, or if they are not reserved words, you should be able to treat them as identifiers, okay, or if they are constants, you should be able to read out the entire constant. In this case, for example, a string of digits representing an integer, or a string of, or a plus or minus followed by a string of digits representing an integer. So then you would look at the entire thing as a single unit. So a scanner typically takes a file of characters and gives you a file of words, or actually what they are known as so you have the user program is just a file of characters, and what you get is a file of lexemes. Yeah, the word file is used in a very general fashion. I mean, it does not mean a disk file. It means any unbounded sequence, ordered sequence of objects. Yeah, so the process of scanning converts a file of characters into a file of lexemes, and then the process of parsing actually takes over the handling. So that's one reason why I have not worried too much about for example these reserved words. So what I'm saying is the process of scanning would have created a single lexeme out of all these. All these things are a single unit. Yeah, and they will after scanning they would lose the status of being a string of characters. There would be some single unit in the form of some structured an element of some structured data type which gives the identification as to what this unit is. Okay, so it could be an index into a table which says that, and with other details like it's a reserved word or it's an identifier or it's a constant. Its type in a more complicated language, whether it's an integer type or so on, will be filled in later, maybe after the area of after the process of parsing and so on is through. So you will actually create a huge table of the amount of information that you have to extract from the program through all the process of compiling and keep it for use for checking, for example, type checking, runtime type checks, compile time type checks, to detect undeclared variables, which is also a good way of detecting spelling mistakes, right. So all these terminal symbols will actually become single units in some table, and the file of lexemes will just be a single unit which gives an index into the table. Yeah, okay, so that table is resident always in memory for reference during the process of compiling. For example, you have to check various context sensitive issues like, has it been declared before, right? If it has been declared, what is the type? Is it being assigned the right type? Is it being used in an expression of the right type? So you require this table of information for each identifier, reserved word, or each lexeme to know whether it's being used correctly in the program, right? So this is the syntax of the language, and we will get on in future to defining the semantics of the language. Okay. So we'll start the next lecture with the basic notions of semantics, and we will then add on to this toy language new features and see how they have to be defined. The syntactic definitions of these new features is not very critical because you have all the basic material. As long as you can parenthesize expressions, as long as you can parenthesize the new features that you're introducing without ambiguity, or as long as you can define them in some reasonably good syntax, it's not very important how they look. It's more important how the abstract syntax trees look and what meaning you give to the abstract syntax trees. Yeah, thank you.